Thank you very much, everybody. Welcome to Subsidence and Deformation 1. Let's make a start now, even though we've got a few people coming in, just so that we don't overrun into lunchtime. I know how keen everybody will be for food. So with that, can we have our first presenter down, please? That is Soo-Ki Lee from Kangwon National University.
Hello everyone, my name is Soo-Ki Lee from Kangwon University, South Korea. Today I present our research. Title is Iron Mining Induced Substance. Mapping. That's okay. North Korea derived by improved combination scatter with optimized point scatterers. We called ICOPs for insert time series analysis. Too far? Okay. This is study area. Musan mining site. Musan open pit mine, North Korea, close to Chinese border, which is located in Musan-gun, North Samgyeong province. Musan mining, also known as one of big open pit mining, the Korean peninsula with the topography. This mining site has hilly topography with high elevation area. In the figure, we represent the time series images of Musan mining site from 2000 to 2021 derived by optical imaging from Landsat 7 and 8 satellite. Mining surface deformation refer to the changes in the surface level caused by subsurface mining activities. These changes can affect environmental and social impacts, including ground substance, land instability, and damage to infrastructure. To mitigate the effects of surface deformation, mining companies generally employ various ways such as monitoring of substance and implementation of mitigation measures during the mining process. So we suggest two topics in order to monitoring of mining site. First, estimation of elevation changes using DEM. Second, time series analysis based on IPOPs. In this research, we use two of DEM as the topography reference for generating DINSAR. Besides, the DEM will be used to evaluate the change of topography condition in the study area. This table information of this table show information of DEM in this research. We use SRTM DEM. Acquisition date is 2000. ALOS DEM acquisition date 26 to 2011. Copernicus DEM acquisition date is 2011 to 2015. So SRTM-DEM minus ALOS-DEM means elevation changes during 2000 to 2011, and also ALOS-DEM minus Copernicus-DEM means elevation changes during 2011 to 2016. Figure show the evaluation site and the western dumping site, eastern dumping site, and elevation changes from 2000 to 2011 are made by subtracting the values in the LSDM from these in the SRTM DM to determine changes that are increasing in the eastern dumping area and west dumping area marked with blue. Elevation change was generated by subtracting value from the Copernicus DM in the ALOS DM during 2011 to 2016. The eastern area has distribution of elevation changes in the northern and southern areas. In the western area, the western area, there is a distribution changes in the northern part in the dumping area. This result is we estimate of volume changes. The iron ore distribution pattern in the Ansan formation is similar to that of Musan group at the Musan mine. The Musan group is considered to be the eastern extension of the Ansan group. In this study, the average density of ore produced at the Musan mine was estimated to be approximately 3.4 times 10 to 3 kilometer per cubic meter over the average density of ore produced from the Ansan formation. So as a result, the estimation mass change in 2000 to 2011 approximate 88.99 megaton in dumping area, and for 2011 to 2016 about 69.87 megaton. This is the second suggest in order to analyze the surface deformation of Musa mining. We use the SAR data from Sentinel-1 event provided by ESA. The Sentinel satellite has visitation repeat of 12 days, which can maintain the temporal resolution on detecting deformation. So, for SAR data was acquired from October 2016 to August 2022, which contained 168 scenes. Also, we use ascending track and 156 paths and 174 plane, and we use the IW mode and VB polarization. We propose the time series method we called ICOPS. Inside time series analysis is a powerful remote sensing technique that can measure surface deformation with high spatial and temporal resolution and has been widely used in various applications. So we propose the use of improved combined scatters interferometry with optimized point scatter. We called ICOPS, time series analysis for INSA application in the continuous monitoring of surface deformation. ICOPS have two key points. First, use of combined scatters. This advantage is highly applicable, such as rural area or agricultural area. And the second, the optimization of point scatters based on the machine learning. And this advantage have improved precision. PS characteristic has known as the page stable target of radar. We know that the vegetated area like the blue box not produce the PS points caused by lack of coherence. So for the area with not vegetated but also not high coherence area maybe have coherence characteristic that can be used to analyze like yellow box. Therefore, we can evaluate they can be used extracted the deformation data to increase the spatial coverage. Pixels with similar signal characteristic result of test on the images become broader than averaged and applied to original pixels. This called distribute scatters DS. After obtaining the DS as complement of PS points, it can be processed with PS points to perform the time series analysis. Along with the PS and DS points could improve the spatial coverage and measurement with maintain the quality of the measurement point. This is our research workflow. We have three main process. First is pre-processing, and then time series analysis, and last optimization processing. The inside pre-processing step include essential registration process and interferogram formation, and these are generated. These formation using single reference and multi-reference format, which will be applied on time series processing. PS processing need a single reference, and then DS processing need multi-reference format, so we make the both them. 네, PS processing uses stems. The PS points analysis was carried out based on the stems algorithm, and stems algorithm based on ADEI. So selection process based on phase characteristics suitable for finding the low amplitude natural target with phase stability. And this figure is PS processing steps and the result of PS points. And the distributed scatter process was processed to enhance the coverage of measurement by we use SHP identification and additive spatial coherence estimation or the temporal coherence estimation. So we use the FASH method and then SHP identification and additive estimation, DS candidate, and find the final DS. The process is started by select and analyze a single pixel, and then the other pixels were also being processed based on fast statistically homogeneous pixels. And those signals are averaged and applied to form a distributed scatter characters based on the statistically homogeneous pixel value. Then estimating additive spatial coherence of possible interprogram. Then DS points was obtained by define the threshold on the spatial and temporal coherence at the last stage. After the PSDS points were determined, we performed unwrap phase and using MCF method or available interferograms. An error estimation also conducted to reduce the error from topographic error and atmospheric condition. Then for time series deformation estimation was carried out by using SVD approach on deformation rate to derive time series deformation measurement. MPD derived from this step will be processed on optimization process. Keep the algorithm. I show the result. Result mean deformation map at the Musan. As a result, Eastern dumping area P1 has experienced constant substance since 2016. It reached a maximum rate of deformation, 18.63 centimeter years in this area. And then P2, Western dumping area P2 has mean surface deformation, 11 centimeter per years was recorded. And after 2016, American census the North Korea sale of mineral resource. So we make the time series analysis. The accumulation of deformation for each year from 2016 to 2022. So profile deformation from A to A that show the deformation increasing from 2017 to 2021, then has slowed in 2022. We show the maximum deformation 121 centimeters. The western dumping profile deformation. Then from line C to C dot has shown the maximum accumulation about 70 centimeters, and D to D dot also shown the maximum deformation 78 centimeters. The western dumping area, known as dumping area, which had traditional sloping dumping from the profile known the center area has soil compaction due to load of the surface, and low slope has accumulation and debris. This is conclusion and discussion. We conduct the analysis mining capacity by evaluate the change of elevation from the DM. ICOPS method has been applied to assess the land substance in Musan mining complex. Integrated of DS points into PS points has increased the coverage of area in long time observation by more than 40%. And distribution of surface deformation in Musan mining was located in eastern dumping and western dumping area. Further analysis showed the substance deformation related with the soil compaction from the dump materials. Thank you for the listening.
Maybe time for one very quick question. Otherwise, we proceed to the next speaker because it's already late. So the next speaker is my co-chair, Rachel Holley. Please, Rachel.
Right, so I have to say this isn't quite what I was planning to present when I wrote the abstract. One of the problems with... Okay, is that any better?
Yeah.
Right, so this isn't quite what I was planning to present when I first wrote the abstract. Unfortunately, one of the problems of having to write abstracts so far in advance. There was something that I was hoping to put in here that I wasn't able to. But actually, the material that I wrote for the abstract and the things that I have in around it are actually a reasonably good overview and recap of some of the issues with elevation models in INSAR. So perhaps in terms of high science, there's the chunk that I can't present and I'm perhaps missing, but I figured these days a lot of people, particularly younger students, are working with SRTM data and global elevation models and haven't necessarily had very much exposure to some of the problems you can get with elevation models in other data sets and with other ways of working. So this is a little bit of a review of some of those issues, particularly relevant to mining areas. So I'm just about old enough to remember before the glory days of the SRTM era, when people were having to do 3-pass INSAR because we didn't have elevation models. So I think I started INSAR the same year that SRTM was released, which ages me somewhat these days. But these days we have lots of global DEMs, we have SRTM, we have GLO30, we have lots of other good information on this. And if we have height errors, we can do stack processing, regression for height, problem solved, right? Not quite so much. So just a very quick recap. The sensitivity to height scales with larger baselines, steeper incidence angles, shorter wavelengths. So this is actually something that starts to become relevant for some of the more recent smaller SAR satellites. They tend to have fairly large baselines. They're mostly X-band, so the shorter wavelength. So actually, that performance with height starts becoming more important. People used to processing Sentinel-1 with the very short, nice, tight baseline tube won't necessarily see some of these issues. But once we start getting into these other data sets, they can and are important. Some of the issues we see, so poor DEM alignment. In this particular case, there's a section of high resolution DEM which was properly aligned. It was mosaicked with a wider, I think, glow 30 DEM around the edges. And because the high resolution had a poor georeference on it, it was made using, I think, local LiDAR data. When the two were mosaicked, they didn't line up. The glow 30 data was offset. And you can see in the image on the left, there's really quite considerable signals along those mountain ridge crests where all of the topography is slightly to the left of where it should be. And on the right, once we did proper alignment, those signals all disappear. Another problem you can have if you have low resolution SAR, DEM data compared to your SAR. So you can end up with the problem where if you have steep, quite sharp topography, you have the tops of all your mountains are missing in the DEM and the bottom of all your valleys are missing in the DEM. And you end up with this really characteristic pattern, which, again, most of you using SRTM data won't have seen. But it's very easy to correct with a higher resolution DEM. And if I flick between the two, you can see that all of that elevation noise disappears. The other problem that we have a lot more in the mining industry in particular, but lots of other applications too, is the topography has actually changed. So Glow 30, the most recent global DEM that we have access to, was made, I think, between 2011 and 2015. For environmental applications, that's pretty good, but you can do an awful lot of mining in the time since then. So you can see in this example, the pit here was partly present in the Glow 30 DEM data set, but there are an awful lot of fringes both in the pit and on the waste piles down in the bottom left. If I reprocess that with a higher resolution recent DEM, you can see that most of that signal disappears. The waste piles, the fringes you see on the waste piles start matching their topography. There has been a little bit of change since even this up-to-date DEM was made. Some of those fringes are actual deformation because those waste piles have uncompacted material which then sinks over time. But you get a really good improvement in your quality by trying to use proper up-to-date DEM data. But why can't we just do a height regression? So these days, most stack processing algorithms allow you to do a regression for your height. Across your stack, you can then correct your topography. It works really nicely when it works. So in this example, it's, I think, a Cosmos SkyMed image. In this area, we were processing across a facility. There wasn't an existing DEM data set that had the facility in it. It was recently built. So we started from scratch with a bare earth ellipsoid, and we generated our own elevation model. And you can see the blue sections on there are the raised pipe racks. So they're the high parts of the facility. And we've essentially mapped out the facility purely using that height-based correction. But there are some limitations to this. So sometimes there won't be enough SAR images in the stack, particularly if you're working with commercial data. You don't have your nice 6 or 12-day Sentinel acquisitions. You have to work with what you've got. You also can't do these stack-based regressions anywhere where you have varying coherence, or where there are periods of time where you don't have coherence. Correlated baselines are another issue. So again, some of the new SAR satellites have issues where the baselines vary through time. And a lot of these processing chains and processing algorithms make the assumption that the baseline distribution averages out over time and is essentially random. Where that isn't the case, you have to start being really careful with what assumptions your processing makes. So the example I've got here is actually a historical example. I stole it straight out of my Fringe 2011 presentation. It's ALOS 1. But the same can be true for quite a lot of the newer SAR satellites. Small baselines, you would expect me to say aren't a problem, and they're not, but they do limit our ability to model the topography. And that's particularly a limitation in urban environments. So sometimes a little bit of baseline is nice, some of the time. And applications where these limitations matter So I'm going to talk quite a lot about mines, but it's also important for things like volcanoes and also for new infrastructure. And any time we're neglecting the impact that DEM changes can have, we're going to be limiting what we can do, particularly for these applications. Mine sites, they're particularly tricky for elevation change, partly because having the mine, the point is to try and change the elevation. But there are lots of different processes that go on. They excavate the pits, but they also have waste piles, stockpiles. TSF is a tailings storage facility, and they are often built sequentially, so every few months to few years, they will raise the level of essentially the dam holding back the mine waste. You often get a lot of co-occurring deformation, so you have both height changes and settlement of dumped material or triggered instability, for example, if you've had a failure in the area before. And you have to have both an algorithm and a data set which allow you to pick apart those different contributions properly. And because different parts of the mine are changing at different times, you'll have intermittent patches of coherence which are incoherent for a short period, pop back into coherence again, but with completely different topography and a completely different motion regime to what they had before. And that will change in one area of the mine at a different time to it does in the next area and the next area. So it's quite a complicated jigsaw puzzle to try and put together. It's also somewhere where really timely results are crucial. We don't have 6 months to sit down and try and pick apart all these contributions because we're trying to do mine safety monitoring to make sure that populations aren't at risk, for example, or workforce aren't at risk. It's really important that we have this data quickly. So there are, of course, alternative DEMs. There are lots of different sources. You can acquire DEMs, say, from airborne data, drones. You'll all have seen the kinds of data sets you have in Google Earth. We can get it from bistatic radar, which is what a lot of the global DEMs tend to be, and also from stereo-optical data acquisitions. So this, for example, I think is a Pleiad image. Stereo-optical, you can use it to refine the elevation model really quite at a very localized scale. Which DEMs you can use depend on what you're trying to do. There are obviously limitations. It's lovely to have really frequent, high-resolution elevation models anytime you want them, but that comes at a cost. So what you're trying to do with that data has to justify the increased cost. But there are also some technical barriers. So things like cloud cover can affect airborne and satellite stereo. There'll be flight restrictions. There's limits on where you have archive coverage. And you also have problems as soon as you start introducing small areas of DEM coverage in sticking them together properly, making sure you've done the mosaicing correctly, georeferencing them properly, and getting them quickly. If you have an area of the mine that has become coherent, you want to be getting an elevation model within, ideally, sort of 11, 12 days for your next SAR acquisition. That's quite a tough requirement, even for the commercial DEM availabilities that we have. And just as an example of what I mean by when an area becomes coherent after a change, this is a tailings storage facility which has recently undergone a dam raise. So they've added material onto the top of an existing tailings dam. And you can see the first image we processed after the change. As soon as the coherence returns, we're getting quite a strong apparent uplift signal, which exactly matches where they've put the new material. Now, we understand what that is, but trying to explain that to a client and putting it through the automated alerting procedures that say, hey, we've got deformation here, obviously doesn't understand why it's seeing that signal. So if we can get a quick, up-to-date DEM and remove that height error, then we get better, easier to use results. Recently, there are more improvements in the availability, the quick availability of those DEMs, for example, often just because satellites are now coming in constellations with faster revisits. So we get down to the point where we could potentially get acquisitions in days rather than having to wait months like we needed to a few years back. But that does, again, rely on things like cloud cover. The other thing we've looked at recently is retrospective studies of tailing storage facilities, for example. A lot of the operators in recent years have become really kind of wide awake and clued up to what's happening with their tailings after some of the terrible dam failures that have occurred. But one of the problems with tailings dams is many of the construction methods mean the older phases are buried underneath the later phases, so they build up on top of existing structures. And if you want to understand the stability of those existing structures underneath, you want to know you're on stable foundations. But sometimes past mine operators didn't keep records, didn't accurately record what they'd done, when they'd done it. So the satellite archive has a lot to add for that. We can go back in time, we can show the operator how their mine was built before they bought it, for example, how the tailings dam was constructed, and also how stable it was before they put anything else on top of it. And that's great, we've got that huge SAR archive going back 30 years, but what we don't always have is DEMS. We have the wide, coarse-scale global DEMS, but it's much better to have data close in time to when the interferograms were produced. We want to have a DEM data set that matches, if possible, at least each time period where nothing changed, or even each interferogram. And so this is an example of a recent study we did. It's a bit of a schematic rather than exact data for unfortunate commercial confidentiality reasons. But basically what we have for this site is split up time periods based on when we know that the surface was changing. So when they were doing these phased dam raises, we can look at the INSAR in time periods between those raises. We can try and find an elevation model that matches those as closely as possible. And then we can get a deformation history for the whole structure throughout a fairly long period of time, but without those DEM artifacts that will skew the interpretation. There are lots of potential sources for those. Once you get into historical data, you have to sometimes start combing around and cherry picking data from here for this time period, data from here for that time period. There are some other sources of frequent historical DEMs in development, and that's one of the things that I unfortunately can't talk about today and hoped to. But in conclusions, so we mustn't forget, I think, that the standard INSAR approaches with a global DEM and a stack-based regression don't always suit things that are frequently changing or have really fine-scale topography, for example, urban applications. And whatever we do with the decisions we make in the future for SAR processing, for example, and SAR data supply, needs to bear in mind the fairly specific needs of these kinds of applications. On that note, we had a discussion, I think, in the Monday session about the co-registered SLC products. And just out of interest, I took one of the examples from my presentation here, and last night very quickly ran it, a very quick test through the processing, and tried geocoding the SAR image with and without the high-res up-to-date DEM, and you can see there's a really large shift in the position of that mine. There might be things that we can then do to try and mitigate that and reverse the geocoding correction to then do the processing, to then geocode it again better. But if you're trying to do rapid monitoring for safety of life applications, that's quite a big barrier to getting timely, accurate, good results that are easy for the mine to understand. So I will leave it there. Thank you very much.
Thank you for the nice presentation. Any questions?
Did you look at some TandemX data? Because with TandemX you get a DEM and you can do the INSAR in time. And this can improve results a lot. I didn't do this for INSAR, but for glacier offset tracking. and got much better results when you instantaneously get the DM together with the user acquisition.
For sure, you absolutely can, yes. And it's a really nice, neat way of doing it. Obviously, commercially, it comes at a cost. Sometimes the application will justify that cost, and when it does, it's really brilliant. But it's nice to have a range of different options for different sites. You can't always get tandem X data where you want it, for example. There are other mission requirements. There are other sensors that aren't TerraSAR X for your SAR data. So it's nice, for sure, that's a really good example when you can use it, but it's nice to have the full range of others as well.
I just had one comment on the co-registered SLC slide. I completely agree, yours is a very specialized case. Maybe you should not be using geocoded SLC for such detailed stuff, but maybe that should not hold up the rest of the community from using that approach. I see this as an extremely specialized analysis, not a very common sort of use case. So it was just a comment on that.
Yeah, for sure. I absolutely see the benefits of the geocoded SLCs for a lot of users, and I wouldn't say don't ever use them. My position on it, I think, personally, would be, as a community, there are enough applications. Mining may be quite specialised, but there's quite a lot of it, particularly in the commercial world. There are also volcanoes and ice applications and a lot of urban INSAR, again, commercially, but also, I think, in academia, looking at building scale deformations and digital twins and engineering models of buildings. And all of those things rely on being able to refine your heights in radar space and get height corrections out, which then affect the geocoding. So we can argue about the size of each of the market sectors, but I guess I'm just saying, don't forget about us.
Okay, it's time to pass to the next speaker, Zara Sadeghi. I hope I pronounced well your name.
Hi everyone. The project that I'm going to talk about today is entitled an INSAR analysis and corner reflector experiments for infrastructure stability monitoring using Sentinel-1 imagery. This project was defined by National Grid and implemented by Spotted, National Grid, and Cranfield University. So, National Grid Energy Transmission owns and maintains the high voltage electricity transmission network in England and Wales. And some movement of the electricity tower can make unacceptable safety hazard, which National Grid is required to correct this movement, which can be very expensive. So in order to avoid this or prevent this, National Grid conducts their own invasive analysis annually to monitor the assets most at risk of movement. So it costs over £6 million per year for monitoring only 1% of their assets. So due to the need for monitoring the health of National Grid assets and the expensive cost of their invasive analysis to monitor their assets, National Grid defined a project to use INSAR for monitoring stability of their assets with at much lower cost and without need to physical access to the assets. So National Grid defined this project and delivered to Spotted to answer these questions. Could a synthetic corner reflector be sized, designed, and installed on assets, such as towers, such that the asset itself becomes a radar reflector? Could a team find National Grid energy transmission assets that can be selected as natural reflectors in selected NGET sites? And question 3, could more than one synthetic radar reflector be installed on a single asset to get multiple asset motion readings from a single asset, for example, to measure the asset motion of each tower leg or each corner of substation? So in order to answer question 1, we designed corner reflectors for NGET assets. In the design phase, we had these assumptions to have sub-centimeter uncertainty in displacement and having signal to clutter ratio equals to 10 decibel for a typical UK rural landscape away from woodland. So these assumptions, using these assumptions, we designed trihedral corner reflectors with a size of inner leg as 70 centimeters. So we also had some special adaptation for installation of the corner reflectors on electricity tower, including mounting for ease of installation to tower and alignment of the corner reflectors towards the specific satellite descending tracks. Also, we installed nets over the corner reflectors to prevent it get filled with debris. Also, we designed drainage holes to prevent it get filled with water. And also a small chain between the corner reflector and tower to prevent falling. So the first test site was NGET D-site test site in the UK, in which we had 2 test towers. So first we installed the first test corner reflector on Tower 1 on 2nd of November 2022 with 100% clear view towards the Sentinel-1, descending Sentinel-1 track. It was track 154. And the second test corner reflector was installed on Tower 2 on 7th of December 2022 with 0% clear view towards the satellite, which was obstructed by the body and arm of the tower. These pictures show the installed corner reflector on the 2 test towers in the NGET test site, in the D-site test site. Before looking at the SAR data, we did some pre-processing steps or some processing steps. So we downloaded Sentinel-1 images of track 154. We downloaded 3 images before installation, 6 images after installation, and 1 image after removing the corner reflector from the tower. And all of the images co-registered with respect to the first image after the corner reflector installation. And all of them geo-referenced using a high-resolution LiDAR DM. So if we look at the SAR image in the area of the installed corner reflector, for 1 image after the installation on the left-hand side, and 1 image before the installation in the middle, we can see the bright signal coming from the corner reflector on the tower. on the amplitude map. And also, if you look at the amplitude time series of that pixel, we can see more than 1.5 times jump in amplitude after the corner reflector installation, and a significant jump of corner reflector after removing, the drop of the amplitude after removing the corner reflector. We think that if we install a bit larger corner reflector on tower, we could have a more strong signal, because in the design phase we assumed UK typical rural background, which is a bit different from the site test side, which was more cluttered and having urban structures. And as we expected for the corner reflector 2 on tower 2, there wasn't any specific clear signal or jump in amplitude value because of the obstruction made by the body of the tower. Also, in order to investigate the impact of corner reflector installation on PS selection of PS insar analysis, we applied conventional PS insar analysis using SARPers and 13 Sentinel-1 images after corner reflector installation, and 15 Sentinel-1 images before corner reflector installation, both from the same descending track. So on these two images, you can see the selected PS pixels over the temporal average of amplitude. So on the right-hand side after the corner reflector installation, and on the left-hand side before. So as you can see, we've got selected PS points at the position of the corner reflector after installation, while we don't have any selected PS pixels in that area, I mean inside the green box. So it means that installing corner reflector on a tower can help us to detect as PS pixels in the PS processing, and then monitor its stability. Also, this is a velocity map of the very small area, and we looked at the amplitude time series and deformation time series of the same pixel. And as you can see, there isn't any specific deformation event for that pixel. And in order to answer question 2, we did a PS analysis using SARPers and Sentinel-1 images in 3 different NGT test sites, which includes the line of towers and also substations. You can see here on the left-hand side, as an example, the velocity map result of one of the sites. And the result of this experiment confirmed that some of the towers can be natural radar reflector and selected as PS pixels because of their orientation relative to the Sentinel-1 satellite, and some of them can't. And as we showed, installation of corner reflector can be helpful to be selected as PS pixel. In order to answer question 3, we installed 3 corner reflectors in a L-shaped format in an open grassy area on the Cranfield University test site. And we implemented 3 different layouts for this L-shaped format to make the corner reflector closer and closer together in both along track and across track direction to find the minimum distance between 2 corner reflector that still can have two distinct signals from the corner reflectors. So we did a similar processing on the SAR images, this time from another descending track 81. 3 images before installation, the corner reflector, and 1 image after each layout installation, all co-registered with respect to the first image after the first layout installation, and georeferenced using a high resolution LiDAR DM. So as I mentioned earlier, we implemented 3 different layouts in an L-shaped design. So we kept the central corner reflector at the same location in each layout, and then decrease the distance between the corner reflector in along track and across track direction to achieve what we wanted. So in the first experiment, we put the corner reflector with 60 meter distance from the central corner reflector in along track direction, and 20 meter distance from the central one in across track direction. So if we look at the first amplitude image of the first image after the first layout, which we named I1, and compare it in the same area before installation, we can see 3 distinct signals related to the 3 installed corner reflectors. Also, we looked at the amplitude time series of the 3 corner reflectors. As you can see, after the installation of the corner reflector, there is a significant jump in the amplitude value. In the second layout, we kept the central corner reflector at the same location and decreased the distance of the corner reflector in along track direction to 30 meter, and also put another corner reflector with 10 meter distance from the central corner reflector in across track direction. And again, if we look at the first image after the second layout, which we named I2, and compare with the image before any corner reflector installation, we can see that we can say there are 2 distinct signals in along track direction, but sounds the signal in across track direction starts to overlap. So if we look at the amplitude time series of the 2 corner reflectors located in along track direction with 30 meter distance, we can see a jump of amplitude at I2, which is the image, SAR image after the second layout. On the left-hand side, you can see the amplitude time series of the central corner reflector. So that's why we've got jump of the amplitude at I1, I2, and I3. Okay, sure. So if you look at the amplitude time series of the bright pixels between the central corner reflector and that one located with 10 meter distance in across track direction, we can see for all of them there are jump of amplitude at I2, but for one of them this jump is larger, which is related to the corner reflector located with a 10 meter distance in across track direction. So it means that the signal between the 2 corner reflectors in across track direction start to overlap. And if in the third layout, we put the 3 corner reflector only in across track direction, kept the central one, put one of them with 5 meter distance and another one with 10 meter distance in opposite direction. If we look at the image I3, which is acquired after the third layout, we can see the signal of this corner reflector is overlapping. So we looked at the amplitude time series of the bright pixels between the central corner reflector and that one located with 10-meter distance. Again, we can see a significant, we can see jump of amplitude at I3 for all of them, but for one of them, this one is more significant, which is related to the corner reflector installed with 10-meter distance. We also looked at the amplitude time series of the central corner reflector, and that one with 5-meter distance. And for both of them, we can see significant jump of amplitude at I3, and the signal overlaps. We also looked at the RGB color composite analysis using the images acquired after each layout. I1 as red, I2 as green, and I3 as blue. This helped us to reassure the location of the central corner reflectors with white color. The corner reflectors located in along track direction in the first and second layouts with red and green color. And in the bluish area, the pixels affected by the corner reflector installed in a third layout in a cross-track direction. So as conclusions, we showed that synthetic corner reflectors can be designed, installed, and used for monitoring of displacement of NGT assets. Some NGT assets like towers can be natural radar reflectors because of their orientation relative to the Sentinel-1 satellite. Design of a larger corner reflector, like with 1 meter inner leg, or an array of small corner reflectors and installation on the NGT towers would improve the signal strength. As long as the spacing is more than approximately 30 meter along track or 10 meter across track, the corner reflectors should be visible as distinct targets. This translates to 1 to 2 corner reflectors per tower, but multiple corner reflectors per substation. It is recommended to investigate how practical could be installation of 2 corner reflectors on an electricity tower with regards to the size of the tower to still have 2 distinct signals for future study. Thanks for your attention. Happy to take any questions.
I think we're running a little bit behind, so unless there's any urgent questions, maybe we could save them for the end. Right, and then our next speaker will be Otmar Frey.
Thank you. Good morning. I want to talk about some activities we have been doing over the last couple of years, and specifically an extension of that on a car-based radar, SAR and INSAR, also from the drones. So you see some pictures here on the title slide where you can see implementations of a L-band SAR system for a repeat pass acquisition. And the main idea is mobile mapping of surface deformation. And I will start out with a quick recap of what we have been doing, mainly with the L-band, and then the extension is basically that we try to do that concurrently with L-band and KU-band. So this is still work in progress, as you will see, with some first results. So the implementation of that sensor configuration, including a KU-band system, and the L-band system is on the right-hand side here. Sorry. So do a quick recap, then show you a bit the motivation why we do L and KU-band concurrently, and show some first results on this simultaneous acquisition, and do a summary and outlook. So we have been doing a couple of demonstrations of this L-band-based the INSAR for surface displacement measurements based on a car, or also with drone experiments. So you see that sort of a summary slide here. I'll pick one of them to show a bit more detail. So this includes surface displacements, a landslide in Switzerland, glacier movements. We also did some tomographic tests with some opportunity baselines that we got with the drone-based acquisitions, which I'm not showing here. So this was already shown previously. I just keep this one here for basically showing you, those who haven't seen that yet, how this system works. So we're driving by on the site on a car, so we need a road. So that's the main disadvantage with this approach, of course. So if you have a road in front of a slope, moving slope, you can use this system. We're driving by, typically taking synthetic capture of a couple of, let's say, 50 meters, 100 meters, 200 meters. And with that, we can produce a high-resolution image, also at L-band, and do this repeatedly to get displacement measurements. This is, I hope this is running if I click here. Yeah, so this is a short overview for this specific site with the data products, so like processing chain to obtain the displacement map. So this is a quite fast-moving landslide in Switzerland, which became more famous in June again because a massive collapse happened. There's a small village close by, so people had to be evacuated. Our measurement is from 2020, so when times were still a bit safer, but already fast-moving. So you see displacements within 4 days up to a couple of centimeters, so it's really fast. So this is the L-band case. So why now L and KU band? So there are several reasons. We think with the L-band system, we have basically successfully demonstrated that we can do mobile mapping of surface displacements. So this is a nice complementary tool to other systems. And there's also in-house, but in other companies or like providers as well, of course, KU-band systems that are stationary or quasi-stationary that are also established to measure surface displacements. So now KU-band doing SAR would be an advantage in terms of getting higher resolution if you're further away, so to complement a bit this resolution loss with the stationary systems. And if we can operate it simultaneously from the same setup on the car, we can, of course, try to benefit also from the two different frequencies. There's for sure different temporal decorrelation times and displacement velocities, sensitivities with the two systems. And we are also interested in just the technical aspect of it because KU-band, the INSAR is, of course, challenging, as we also see later. Is a technical thing we want to tackle because we want to be flexible in terms of having different frequencies for agile platforms such as these. So this is the system we are using. So it's this L-band SAR system, an in-house development, and we are kind of abusing the gamma portable radar interferometer as a SAR system. So you basically have the same back end in terms of the radar, but instead of these long antennas that are rotating, which is the usual setup, we have horn antennas, as you can see here, mounted on the car that we can operate simultaneously with the L-band system. Just a few words on the system characteristics. Both systems are FMCW radars. Technically, both are capable of doing 200 megahertz bandwidth. The thing with the L-band system is that we are not allowed to transmit more than 100 megahertz bandwidth in Switzerland, I think in many other places as well. But technically, you could do also 200 megahertz bandwidth to get a range resolution close to 1 meter with some windowing included. Then, of course, the azimuth resolution depends on your antenna size technically, but in our case, often we don't drive like a full synthetic aperture, so it depends still on the range distance if we go further away, depending on our configuration. So this is also still a bit variable depending on our setup. So this is the first site where we started to do combined L and KU band measurements. We thought it's a nice site. It turned out to be like suboptimal since it's a super steep one in terms of the geometry. It's in the Swiss Alps, and there's actually also some monitoring going on the side with the stationary system with long-term monitoring. So here again, you see just the way we operate the system. So we drive by repeatedly a couple of times every time we're there, but of course also then come back later in time over a couple of months, and we try to build up a time series like this. So I want to start out with some coherence images of that site. So basically, this is a top view of the situation. The car will be driving this direction and viewing towards the slope here. So that's the steep slope. And below, there's a bunch of trees. So to remind you, it's not the same extent. So the KU band is kind of blown up a bit compared to the L band in this view graph. So these trees here correspond to that section down here. The extent of the beam width is different, both in elevation and also in azimuth. That gives a slightly different viewpoint. So the L band system has a 40-degree beam width, so quite large beam width, whereas this is much less in the KU band case. Yeah, so clearly the sensitivity is quite different. So this is a very short interval, 4 minutes. You can see that with L band you have a very, very high coherence, even in most of the vegetated area, whereas this is of course not the case with KU band, but still in the rocky area you get a substantially high coherence, so over a very short time. So this confirms that this is okay for repeat pass, but of course it will be different for longer times, as we will see in a minute. So this is the phase, so I didn't really further process that. So you see in L band it's fairly stable, so there should be no movement within this short time, whereas in KU band we see some artifacts which still are in the processing. So this is just like out of the box, no corrections applied additionally, just topography corrected data. So now if we compare that 4 minutes with a period of 4 months, of course, the situation looks much different. So I picked here a quite extreme case with acquisitions once in winter time, as you can see in the imagery here. And the same situation in summer with grown vegetation and no snow, of course. You can think, of course, that in terms of deformation, this is not an ideal time span in any case because there's different characteristics. But just to look at the coherence, we can see that, of course, with L band, we still have substantial coherence, whereas it goes down really dramatically at KU band. So where you can really see the different behaviors that are expected, but I think are nice to have as a complementary tool with L and higher frequency systems to actually be able to measure the different characteristics of surface displacements and decorrelation. So we have then ongoing campaigns. Actually, this is almost in the same area, a bit further up the valley. So in this area, as in many valleys, the upper parts and several instances are moving in one or the other way. This is basically the first measurements we did at this site. So at this time, first try also with KU band, which did fail at this specific time. So this is between 21 and 22. So also quite some time in between, so half a year. And you can see that in this area, you see a picture on the right-hand side, there's quite a bit of vegetation. And then in the upper part, there's mostly rocky area, but you still see, of course, a bit of snow as well, so where you have decorrelation areas, and also areas with debris that is decorrelating much faster. But you can nicely see the different characteristics of the coherence with this L-band system over the different land cover, and still giving you quite a bit of coherence also in some of the vegetated area over such a long time period. I just picked, or actually a colleague, Rafi Gadouf, who's a co-author of the paper and was measuring with me a lot over there, has picked a few close-ups in the upper area. So this is taken from somewhere up here. And this is just to highlight the nice feature about the resolution we get with this L-band system. So even like a couple of kilometers away, you get substantial resolution to actually see features. So here is a debris area where you have much more decorrelation than in the other area next by. And potentially there are also some deformation patterns than visible, but in this case it's mostly decorrelating because there's too much change over time. So now this is, as promised, now really this concurrent L and KU band imagery from the same site. So this is also to show you a bit the different extent of the imagery that we see. So on the left-hand side, the L bands are, as I said, it's 40 degree azimuth beam width. So we get quite a wide view, even though we're not driving a very long distance. So in this case, it's something like 100 meters, and the road is actually a bit curvy. And you see that also this leads to some, let's say, variation in the backscatter. This is not corrected here. In the KU band case, you can see that really nicely. Yeah. What you also see is that for KU band, we have substantially higher resolution. This comes, of course, by the twice as much bandwidth in range, but also the azimuth resolution is better, depending a bit on the situation of the geometry, of course. So now looking at some phase and coherence for these imagery. So I picked a few. So we're starting to build up a time series, as I said. So we were like measuring like 3 times now, like with half-a-year intervals, and of course every time we're there we also do a couple of measurements. So this is a time span for the L-band data of 1 hour and 17 minutes of the same area. So where you see the coherence and the phase on the left-hand side. Again, here the phase is not further treated, so this is just topography correct that we process directly to the digital elevation model using a time domain back projection approach, using accurate navigation. So this is basically what comes out of that, then doing just the interferogram, so no other phase corrections applied so far. Then the same thing for the KU band imagery, and you can see, of course, I flip forth and back a bit here. The dramatic difference, of course, in the coherence for this particular area, because the lower parts here are vegetated areas, so forested areas, but you can see that in the upper parts, in the rocky areas, you get still very good coherence, and of course some phase patterns. So there's you see a good phase measurement, but of course it's not something you can use directly for deformation. So there's a lot of work to do. I think it's mostly related to already atmospheric, but also of course maybe some remaining baselines that we have since we're driving on a relatively narrow road. We have a more or less okay repeat pass, but still, of course, it's not perfect zero baseline. And then you get easily some fringes, and there may also be some still motion-induced areas that need to be corrected. So didn't check for that for this particular case yet. So now looking at the longer time span, or 4 months, for this site here, as you see that for L-band, as previously, we have still quite a nice coherence, and also the phase looks very smooth. So this is easy to correct. Also not corrected here is of course not displacement, but mostly atmosphere probably. But this is not problematic to correct. So this is similar as what we had to do for this Brienz landslide case, where we can easily correct that and then actually look at displacements. Okay. So this is the KU band case, and I switch forth and back again here. So you can see 4 months here in this case is very low coherence, of course, a KU band in the vegetated area. There's still some phase patterns that you can retrieve in the upper parts of the rocky areas, but the coherence is also pretty low there. This is partially due to different characteristics still, because one of them is in June and the other one is in October, so there's a good chance there had been some snowfall in between already, so there's also natural cause for that. Then coming back to let's say the October within 1 day, 17 minutes, so very, very short time span. Just to have a look at this as well, because that looks much nicer for KU band and shows complementarity. So L band is a very clean phase, super high coherence. Everything looks great. And also at KU band, you have quite good coherence, except of course in the forested areas. And the phase pattern in this case also looks a bit smoother, so probably less atmosphere in October. So this is something we can work with, but it's of course a start into this direction. So to summarize these activities, we can do high-resolution repeat paths, the INSAR from Agile platforms at L-band for sure. So this is operational, you could say. We need a decent INS GNSS. At KU band, we're sort of on track, but not really there yet to really use that as a tool. But we believe this is something we can get working for specific applications, complementary to the L-band case. We get good SAR focusing quality with our approach, high resolution imagery, so I think we're on track there. There's still some work to do with the KU band to do some residual corrections. The behavior is as expected, so this is not big news there, but I think it's a nice tool to have and actually to have the two frequency options to do some measurements, different characteristics in terms of the correlation and displacement sensitivities. Just a bit of outlook. So we're working further on building up this time series and doing tests, also with different people interested in that, towards developing services in this direction as well. And on the development side, there's also a development led by Charles Werner, which is downsizing the L-band system so that it can actually be put on smaller drones, not such a large one as we were flying. So total payload will be below 8 kilograms for quadcopter drones and also other platforms. With that, I would like to close, and thanks a lot for your attention.
Thank you for the nice presentation. Time for one quick question.
Hello. I saw in the Cuban image that the intensity of the Cuban image in the middle has a drop in the intensity. Can you
speak louder?
Sorry. In the image, I don't remember the number of the slide, but in the intensity image of the Cuban radar,
yeah,
I saw that you have it seems like there is a slight drop of the intensity in the middle, like in the middle of the
yes.
Of the valley, of the mountain. Sorry. Do you have any explanation for this, or?
Yeah. So I mean, this is the road is quite curvy. So and we don't really correct we don't really correct for everything in that sense. So we do like a weighting in terms of how fast we drive. But if you're really rotating the antenna a lot, then yeah, this is what you see there. So with the L-band, it's less pronounced because the beam pattern is more graceful, let's say. Yeah.
Okay. Thank you.
Maybe if you scream, it's still possible. Yes. So this is, you can actually check because it's, since a couple of years, it's available for everyone. So it's by the Swiss Office of Topography. It's a dam that is originally based on LiDAR dams, LiDAR acquisitions, but it's also updated with optical photogrammetry. This one is probably 1 meter spacing. So originally it was 2 meter spacing. This is even better now, so they upgraded. I'm not exactly sure. So it's pretty good. Elevation should be, I don't know, around 1 meter, depending, of course, on where you are. So it's pretty good digital elevation model. And it's also something you actually need, of course, to get good results.
Thank you. I think we need to move on now. So I'd like to welcome our next speaker, Manuela Bonaro.
Okay, good morning to everybody, and thank you for staying here so long before lunchtime. So today I'm going to talk about the main results that we have achieved through an extensive national scale INSAR processing made through the full resolution parallel small baseline subset approach. For the analysis, investigation of the deformation phenomena relevant to the built-up environment, relevant to the main Italian cities of the Italian territory, for sure. This has been done through the exploitation of HPC infrastructures, in particular GPU parallel processing techniques. And the main results I'm going to show you are relevant to the exploitation of large multi-temporal SLC data stacks relevant to X-band Cosmos Schemed datasets, but I'm going to show you also the preliminary first results relevant to SAOCOM-1 data, L-band SAOCOM data. So we will just say a few words about the full resolution piece bus processing chain. We will focus on the parallel implementation. Then we will move on the experimental part, so the results achieved on some of the main Italian cities. There is no room to talk about in details about the overall results we have achieved, so we will focus on some representative case studies, and then we will move on the developments. I have, there is no time to talk about, and there is no reason to talk about the advanced NDSR technique relevant to, called small baseline subset, because I'm pretty sure that you know the capabilities that are well demonstrated over the last 20 years for this very important DINSAR approach for detecting deformation relevant to both natural and anthropic hazard scenarios. Basically, we start from a large stack of SAR images that are properly combined in order to generate a large number of small baseline, small in time and space interferograms. They are combined together and inverted in order to get two main products, the mean deformation velocity maps, and for each single covariant pixel, the deformation time series. But one key point of this bus approach that is the core of my presentation is the fact that this bus can be applied in two different spatial resolutions. The medium spatial resolution and the full spatial resolution that exploits multi-look and full resolution DINSAR stacks, respectively. The first one, the medium, exploits a multi-look interferogram and analyzes deformation phenomena relevant to large areas, so regional scale analysis, in particular volcanic seismic events, while the second one, which is the focus of my talk, will be exploits full resolution data stacks and is able to detect localized displacements relevant to single buildings and infrastructures. This is the simplified block diagram of the full resolution bus insert technique, which basically consists in four main blocks. We start from two stacks of DINSAR interferogram, the full resolution interferograms, and then we exploit also all the low pass components coming from the low resolution piece bus processing, which are relevant to deformation, orbital ramps, and atmospheric phase screams. They are put together and subtracted modulo 2 pi to the full resolution interferogram in order to get what we call HP high pass residual interferograms. Then the residual interferogram, HP, the residual interferograms are based on two different phase components, linear and nonlinear phase components. For the estimation of the linear phase components, we exploit a model, linear model, through the phase unwrapping step performed on the second block, the central one, the heaviest from a computational point of view. And the linear phases components are relevant to the velocity, the topography, the residual topography with respect to the DM, the thermal dilation, which is basically associated to metallic infrastructure, and whenever available, we have also some the azimuthal position, which depends on the availability of various Doppler centroid on the data stacks. So we retrieve these linear phase components through the phase model, and once found these components, they are modulo 2 pi subtracted to the HP residual interferograms in order to get the nonlinear phase components. Okay, this one. And the linear phase components are, the non-linear phase components are assumed to be already unwrapped, so we don't need to apply another phase unwrapping step, and so we just can go to the inversion of the system and to find the HP deformation time series. Once found the deformation time series, we can sum up all the linear, non-linear, and low-pass deformation time series in order to get the full resolution deformation time series. Okay, so this seems to be quite straightforward, but for sure we need to face some drawbacks related to the very large increase of the available data stacks, full resolution stacks, both in terms of number of images to process and number of pixels to process because of the size of the images. So we have to face about the problem relevant to the exponential growth of the processing time and the consequent data processing load and complexity. So to face this problem, we need to adopt advanced HPC solutions, infrastructures, and in this case, we adopted mainly the GPU power, the GPU-based parallel solutions that are particularly important in the central blocks, the red and the green one, because they are, as I anticipated, they are the heaviest from a computational point of view. So they are also characterized by a pixel granularity. It means that every single pixel can be implemented, can be solved in a separate way. So they are particularly suitable to be used with the GPUs-based parallel solutions. And so in this case, we speed up the processing and we move from weeks of processing to, let's say, a few hours to process the overall full frame, getting high scalability and the computing performance without losing the accuracy of the algorithm, because we didn't modify the algorithm, but only the implementation, moving from CPU-only based to CPU-GPU based. And so on one side, we have the parallel techniques, the HPC infrastructure. On the other side, we need to have data, so very high resolution data. And in this case, we can fully benefit from the availability of X-band Cosmos Skymed, the first and second generation data set all over the Italian territory through the Map Italy project. In this case, we had 4 satellites of the first generation. Unfortunately, one, CSK3, we missed one satellite in October 2022, but thanks to the availability of the recent 2 satellites of second generation, we can go on with the processing and make very long-term deformation time series, benefiting from the overall data set starting from 2009. And so we here move to the experimental part. So we are going to show the main results that we have achieved throughout the Italian territory by exploiting full resolution piece-bus analysis and Cosmos Skymed first and second generation dataset. For sure, we don't have space to talk about in details of all the deformation phenomena that we have achieved, but we can just zoom in some particular specific test cases that are representative to our analysis. So let's start with the first data set, which is our favorite one, the Napoli Bay Area, because we live and work there. So we are also center of competence for the Italian Civil Protection Department, and in this case, we continuously monitor the Campi Flegrei caldera. We can see here the different behaviors seen from ascending and descending orbits because of the east-west deformation components of the caldera, but in this case, we are not interested. Here we have an example of the uplift of the last 13 years of the deformation of the caldera, Campi Flegrei caldera. But in this case, we are more interested in analyzing the formation relevant to the built-up environment, so localized displacement. And now we are going to zoom in some specific cases. For example, here we have the connection of the high speed with the Napoli rail station. And we can see the plot relevant to the deformation time series that we have achieved through CSK, CSG datasets. I have highlighted in black and red the triangles, the different data, just to understand the perfect overlapping between the acquisition and the capability of continuously monitoring the dataset, the investigated phenomena. Here we have another example on the northern part of the Capodichino airport. In this case, we don't have a linear behavior. We have a non-linear behavior with a lowering of the deformation up around 2016. Here we have, let's move to another data set in Roma, central Italy, the capital of our territory, and we have exploited both ascending and descending orbits, always for a civil protection department within the agreement between IREA and civil protection department, but in this case with another intent, that was the writing of the guideline for the use of DINSAR measurements for the good interpretation of the deformation for built-up environment analysis. In this case, we can retrieve many different deformation phenomena. For example, the Roma Fiumicino Airport subsidence, the almost linear deformation pattern of the Grande Raccordo Anulare, we can see due to the compaction of the soil in that area that is coming to the infrastructure. Another, in this case, non-linear behavior due to the thermal dilation of a metallic structure in the central part of Rome. Or for the descending orbits, the deformation path of the Roma Fiumicino Airport. We can see the clear non-linear behavior. Now let's move to a northern case study, Venetia, that is particularly important for its heritage, so cultural and historical heritage. For the island, main island, we can see the fish-shaped island. We don't see any clear deformation behavior, but if we zoom in, we can see some spot of deformation in specific structure or single buildings. Here, the case of the hospital close to the northern part of the island. But here, for sure, we focus on some infrastructure, big infrastructures. We have the MOSE, that is the connection between the island and the Adriatic Sea. We can see very important deformation behavior, so some point of the structures. And now we have to analyze also not only cities, main cities, but also small towns, for example, La Spezia, that is particularly interesting for after the collapse of the river bridge Magra, occurred in 2020. And so for this one, we have investigated both ascending and descending orbits. And we can see the different behavior, blue and red, due to the presence of east-west components and due to the deformation relevant to the landslide. The body of the landslide is pushing towards the right shoulder of the bridge. And we assume that this kind of behavior, this kind of movement is the responsible of the uplift of the bridge and of the failure of the bridge, as we can see in this picture. And the last case, just to go throughout the Italian boot, so from north to south, the Catania case study, we can see the clear behavior relevant to the Etna, Mount Etna volcano, but also in this case we are more interested in some localized deformation, as in this case the Catania Harbor. So many cases where the X-band satellites works very fine and many deformation phenomena that are detected, but we have also some cases where X-band is not completely useful to detect the deformation, as in this case. Here we have the Ponte della Musica bridge, and we can see that the bridge, the deck of the bridge is blind, so X-band is not useful, is not capable to detect the deformation. Maybe because of some strong deformation behavior or some vibrational effects. We don't know the causes, but we decided to move on L-band investigation through SAOCOM-1 constellation. That is the Argentinian constellation in cooperation with the Italian Cosmos SkyMed and Italian Space Agency. Through strip map data with 5 meters of spatial resolution and 23 centimeters, we made a processing on the same area. For sure, in this case, the time frame is different because it's only 3 years, 2020, 2023. But we can see that the deck is full of points, and we can also detect some deformations relevant to the thermal behavior of the bridge, of some metallic structures of the bridge. And so we have been encouraged to move on, and these are the very recent results with L-band SAOCOM-1 data on the Napoli case study. We showed these descending orbits just to make a comparison between what we get in Cosmos SkyMed. We can see that this area, this red area that is corresponding to a trash loading. We can see here the zoom-in view, okay. It was not possible to detect through Cosmos SkyMed, maybe because the deformation behavior is quite big. We are talking about 25 centimeters in almost 3 years. So maybe because of the phase unwrapping problems, X-band was not very good. And in this case, L-band can give us a very big help. So moving to the conclusion. Before concluding, just further developments relevant to the new planned X-band constellation throughout within the PNRR framework. Italy is going to launch in 2026 a new constellation of X-band made of 10 satellites. But what is very important in this case is that we are not talking about sun-synchronous orbits, but we are talking about medium inclination orbits. We can see here the main characteristics. So thanks to this characteristic, IRIA CNR started some simulation on these datasets. And for example, we made a simulation considering 6 satellites with a medium inclination orbit of 49 degrees and 6-day repeat pass, and these are the results. So we can get some more information on the deformation, also because we can get some information relevant to the north component that at the moment is not easy to detect with sun-synchronous orbit. So this can be very encouraging for us for getting in the future, maybe by benefiting from both CSK, CSG and IRID data, also to get the full 3D deformation field of, for example, the Italian territory. So we are waiting for the new constellation, and meanwhile, thank you very much.
Thank you for the presentation. One question.
I just didn't catch it on your last slide. You had the 10 satellites. You had 6 + 4. Was that 6 sun-synchronous and 4 mid-inclination? Is that the distinction?
This one are medium inclination.
Yeah, like the top bullet says 10 satellites, 6 + 4. What's the difference between
No,
the 6
they
and
are
the
all
4?
medium inclination orbits.
They're all mid-inclination. Okay.
Yes, they are going to be planned in this way. The difference is because they are going to launch 6 in the next years, and then we are going to they are going to decide on launching also the next 4. But the overall system is medium inclination orbit. At least what they are going to, they are planning.
Okay, thank you.
It's a completely different idea because we need to get some more information on the deformation. And so we want to benefit from that.
Okay, I think we need. You have another question? Very quick.
The new, as you can see, is around 23, 30 kilometers. But we can, the coverage,
The question
the ground
is
coverage.
all over the world? Or?
No, Italian, sorry. The temporal, the ground coverage in the world, no, for now is for the Italian territory. There are some spot areas, depends on because they are going to launch like a fixed number of satellites that cover the Italian territory. If they want to, if needed, they can move some satellites to other specific test sites, but they have to be, for example, for military reason or some other stuff. So, but the aim is the Italian territory.
Anyway, maybe this will be also decided
exactly.
in the future. What will be the acquisition policy will be decided probably in the future.
Yeah.
Anyway, I think we need to close this session. Thank you to everybody, and have a good lunch.